Hello students, this is your Professor Dr. Sharma. So in this lecture series, I'll be discussing about the electricity and magnetisms, collectively called electromagnetisms. Electric and magnetic force, we'll be discussing about electric and magnetic field. So this is the same kind of force, electromagnetic force, but two different manifestations we'll see in this nature. Let's begin with the historical background of the electricity. Okay, so flow of the electron we call the electricity. So to understand about the electricity, you need to understand about charges, right? What do you mean by charges? So to understand about the charge, okay, we have to go back into the Big Bang. So before Big Bang, we don't know what was there. So after Big Bang, when we believe that time began, and then small particles we call the subatomic particles, elementary particle, we can say that elementary particles start to form, just like electrons, quark. Then combination of the different quark created basically the protons and neutron. And once you have electron, proton and neutron, then atom is created. When atom is created, then elements are created, then compounds are created, and then this whole universe, this physical world is created in this way. So you can see here, for example, in electron, proton and neutrons, the electron is a negatively charged particle, we can say that, but proton and neutrons remain at the center. They bond to each other to make a nucleus, and around which you can see the electrons start to revolve, right? So if you look at the charges, their masses, their numbers, what you can get is number of electrons is always equal to the number of protons in nature, right? Anything in this physical world which is composed by the atoms, basically they are electrically neutral, because nature designed in such a way that total charge of this universe remains zero. When I say that universe began with nothing, Big Bang happened, and then particles emerged, this universe created. So when I say nothing, created from nothing means something. Nothing means something. If I write zero, let me write down zero, and I try to convince you zero is something, definitely you will not convince. But when I say I have minus 1000 and plus 1000, which is also zero, it is nothing, but nothing is something. Minus 1000 plus 1000, minus 200 plus 200. In the same way, the nature created the object basically electrically neutral. Number of proton and number of electrons equal, because each has the charge we call 1.6 10 to the power 19 coulomb, but electron have the negative charges and the proton have the positive charge, but magnitude of the charge is equal. Okay, then when we look at the mass of electron, proton and neutron, okay, mass of the electron, mass of the proton and mass of the neutron, you will see mass of the neutron is so much higher than when you add the mass of proton and mass of electron. Why? Neutron is so heavier and also neutral. Because this nature always wants balance. This nature wants the protons always stick with the neutron and electron always revolve around that. The motions and the electron. That's why electron has negligible mass. You can see the mass of the electrons is always 9.1 10 to the power minus 31 kilogram. But mass of proton and mass of neutron, if you look at that, mass of neutron is so much heavier. The fundamental properties in this nature. The fundamental properties in this nature. When you put something in somewhere in non-equilibrium situation, and after some time it will attain its equilibrium situation, equilibrium condition. Means it always wants to remain in the lowest state. This is the nature. In the same way, proton, electron, neutrons were created in such a way that neutron remains neutral, proton and electron remains charged. And this validates, this validates the conservation of charges. So in classical mechanics, in last semester, you learned about conservation of energy, conservation of momentum, conservation of mass. In the same way, conservation of charges cannot be created nor be destroyed. It can be transformed from one place to another place. It can be transferred from one object to the another object. Suppose, let me write down. The question is here. Objects are electrically neutral, right? So each objects are made from the electron, proton and neutron, you know that. Suppose this bench has electron and proton. Electron is negatively charged, proton is positively charged. But you did not see there are any kind of net charges. There are any net charges available there. Net charge is zero. Because positive and negative charges equal, they cancel to each other. Finally, the net charge becomes zero. But when you remove the electron, when you remove the charges from this table to the another objects, then imbalance of the charge happen. Generally, electrons are movables. They are away from the nucleus. They are revolving around the nucleus. To far away from the nucleus, the attractions with the nucleus becomes weaker and weaker when you apply certain amount of forces, when you create the bonds, then they can be easily transferable, easily movable, right? But the nature, the fundamental feature of this nature is when you remove the electrons or added the electron to the objects, then imbalance of the charge happen. And you can remove or edit the electrons by different way. We will be discussing about that way later. For example, right now we are going to discuss about, for example, charge of an electron is 1.6 times 10 to the power minus 19 coulomb. Coulomb is the unit of the charge. Suppose in wire you have 3.2 times 10 to the power 19 coulomb of charge. We call the Q. Total number of charge is Q, is flowing in a wire. Then how many electrons are flowing in this wire? Suppose you have a wire and you measure the current here and you measure the current flowing in this wire is 3.2 times 10 to the power minus 19 coulomb. So how many electrons are flowing here? So you know Q is always equal to the number of electrons added or removed, or number of electrons moving or flowing in a wire, and charge of an electron. So number of electron is always the charge times charge of a single electron. So total charge is 3.2 times 10 to the power minus 19 coulomb, and charge of a single electron is 1.6 10 to the power minus 19 coulomb. So total number of electrons flowing in this wire is 2. When I say 1 coulomb of charge is flowing, in place of the 3.2 times 10 to the power minus 19 coulomb, if I say 1 coulomb of charge is flowing in this wire, then if you measure the number of electrons, you will have large number of electrons that are flowing in this wire. So 1 coulomb of charge is very high amount of charge. Here, I want to emphasize one point. When you remove a charge, when you remove an electrons from one object or add an electron to that object, so you have to remove the integer value of the electrons. You can remove 1 electrons, you can remove 2 electrons, you can remove 3 electrons, you can remove 4 electrons, you can remove 5 electrons, and so on. That must be the whole number, because charge is quantized. You cannot remove, you cannot add 1.5 electrons, because the electron are the fundamental particle, elementary particles. You cannot divide further. You cannot cut it into smaller pieces. That's why number of electrons times charge of a single electron gives the total charge flowing in the conductor or any object. Now, the addition or removal of electrons can be done by 2 different ways. So that's we call the transfer of charges. You can transfer not only the electrons, you can transfer also proton, positively charged. So transfer of charges. You can transfer charges in 2 different ways. Number 1, transfer by contact. And you can transfer by using induction. Suppose you have a woolen cloth, woolen shirt you have, and you bring a balloon. When you rub the balloon with the woolen shirt, woolen cloth, then electrons are transferred from that woolen cloth to the balloon. Then cloth becomes positively charged because electrons are removed from there. The number of protons becomes greater than the number of electrons in that woolen shirt. At the same time, the balloon gains more electrons from the woolen shirt, woolen cloth, and it has more number of electrons than proton, then it becomes negatively charged. So by contact, by rubbing the object, you can transfer the charges. So let's take a simple example. If you have a metal sphere, initially this metal sphere has 4 charges. Let's say it has 4 positive charges and 4 negative charges. Initially it is electrically neutral. Let's suppose that. Then you can bring a rod which is negatively charged. When you brought this negatively charged rod here and start to rub, here, then what happened? Look at it. These negatively charged electrons from the rod will goes into the, when you interact this rod and the sphere, then electrons are transferred from the rod. Suppose these electrons goes in another side here. Now what happens? Now you remove the rod. Now this sphere becomes negatively charged. Look at here. You have four protons, and you have 1, 2, 3, 4 electrons. They neutralize to each other, but 3 more electrons present there than the proton. So then the metal sphere becomes negatively charged. Right? This metal sphere becomes negatively charged. So now this metal sphere becomes negatively charged. That's how you transfer the charges using the contact. What happens when you connect this metal sphere by using the wire to the ground? Then these electrons will flow to the ground. And then only metal sphere has positive charge remain. Now this metallic sphere becomes positively charged. In this way you can transfer the charges by using contact. But there is another way to transfer the charges, which we call the electrostatic induction. Let's discuss about this in brief. Okay? Electrostatic induction. Transfer of charges using electrostatic induction. Let's take the same example. You have a metal sphere. It has some positive, negative charges, positive, negative charges, positive, negative charges. Electrically neutral initially, which is standing on the ground, which is insulated. This is insulated. So that you want to prevent these charges escaping from the metal sphere. Otherwise our earth is also charged. It sucks the electrons from here. Then in this time you take a rod which is negatively charged. You can take positively charged also. But you are not keeping them in contact with each other. Without contacting, what happens to this metallic sphere? Because opposite charges repel and similar charges repel and opposite charges attract to each other. So what happens? When you plot this rod nearby this sphere, then the distribution of the charges like this way. Here is a rod with negative charges. Then positive charges comes nearby this side, the surface of the metal sphere, nearby the negative charges. And negative charges in the metal spheres, they go far away, because these electrons repels these electrons and these electrons goes in this way. They go in this way. Okay. The distribution of the charges is altered, is changed. Now, you put the rod here. Now, you connect this metal sphere with the earth using a wire. We call the ground, right? Earthing. Then what happens? Then you remove the rod. All of these electrons will flow to the ground, and only the spheres has positive charges remain. It becomes positively charged. So in this way you can transfer the charges. In this way you can make a positively charged object, negatively charged object. So positively charged means excess protons are remain than the electrons in an object. And the negatively charged means excess electrons presence than the protons. Means adding electrons you can make any objects negatively charged. And leaving means the removing electrons from any objects you generally makes the objects positively charged. So that's all today. So next time we'll be discussing little bit about the electric field.